This example will compare linear growth and decay and exponential growth and decay given 4 different scenarios. This example shows that a new charter school, when it first opened, had 700 students enrolled. Our job is to use function notation to write a formula for the function n of t, which represents the number of students enrolled in this charter school after t years. In the first of 4 scenarios, enrollment increases by 20 students per year. Compare that with part B, where it still is increasing, but at a rate of 20% per year. When anything grows or decays the same amount each year, like 20 students per year, the growth or decay is described as being linear. When anything changes the same percentage each year, like problem B, that growth or decay is described as being exponential. The equation used for linear and exponential are completely different. One way to write a linear equation is y equals b plus mx, where b is the initial value and m is the rate of change. In our example, the initial value was the initial number of students enrolled, which was 700. M is always how fast something's changing, and if you have a situation that is growing, your slope or m value has to be positive. I'll say greater than 0. If ever you have a situation where something's decreasing, or we'll say that's decay, you have to have a negative slope, or I could write m as less than 0. In our problem, we have that the enrollment's increasing, so we need to have a positive m value, so we'll have a positive slope, and m represents the rate of change. The enrollment's changing 20 students per year, so we will write 20. So this is a linear equation that describes this scenario, but it doesn't have the correct input and output variables. In our scenario, our input variable was supposed to be t for years, so where I had the letter x, I should replace that with the letter t. Also, I used the output variable of y, where we were supposed to have the output variable that represented the enrollment as n of t. So I'm going to replace the letter y with n of t. The directions are to use function notation. I have, that's this right here. I've used the correct variables, so this does represent a formula, n of t, that represents the number of students enrolled after t years. As a check, you might plug in t equals 0, because after 0 years, the school just opened, and you'll find that if you plug in t equals 0, you'll get the 700 students, as described in the problem. I'm going to leave this as my answer, but I'd like to point out that you may sometimes see a linear equation written as mx plus b rather than b plus mx. Remember that addition is commutative, so the order in which you add can be switched without changing the answer. So if you wrote your answer n of t equals 20t plus 700, that would be fine as well. Either is acceptable. In problem B, since the growth was represented as a constant percent change, I noted that this would be considered exponential growth, and I also said the form would be completely different. The equation for an exponential is y equals ab to the x. This time it's the letter a that represents the initial value, and b will be what's called a growth or decay factor. Let me start by just writing down my initial value. It's the same as before. They started with 700 students. I need to find the value of b to complete the equation. One way to find the value of b is to take our rate of 20% and write it as a decimal, which would be, see the decimal points here, if you move it left twice, you'd have 0.2, or if you like, you could write it as 0.20. And then use the formula for growth. Since it's growing, use the formula b is equal to 1 plus r, where r is the rate as a decimal. Just as a plausibility check, you should know that exponential growth can only happen if your b value comes out to be bigger than 1. If you take 1 and add our r value, which is, as a decimal, the rate is 0.20, you get a b value of 1.20, which is bigger than 1, and it represents 20% growth. Just as before, this equation models my scenario, but did not use function notation. So like before, I will take the output variable y and replace it with n of t. And remember, my input variable x was actually supposed to be t. So this is a formula that represents the number of students enrolled in this charter school after t years. As a plausibility check, you could replace t with 0. That would represent the enrollment after 0 years, meaning the initial enrollment, and you would see that you'd get 700. In fact, plugging in t equals 0, I know that 1.20 to the 0 power is 1, and 1 times 700 is 700. So this model does give an initial enrollment of 700 students when t is 0. So I'm going to leave this as my final answer and move on to part C. So remember that in parts C and D, we also have an initial enrollment of 700. When I read these scenarios, I'm careful to pay attention to whether the rate of change is given as students per year or percentage per year. Since in part C, the enrollment decreases the same amount, not the same percentage each year, this would be linear. And over here, it's decreasing by the same percentage each year, not the same number of students each year. That means this will be exponential. So as before, since I have linear growth or decay, I will write y equals b plus mx to start. Remember that in linear, b is the initial value, which hasn't changed in the problem. There were 700 students initially. Now I just have to be careful. This time we're not increasing 20 students per year, we're decreasing 20 students per year. So to get my outputs to go down, for linear that'll only happen if your slope is negative. I'll write that as less than 0. You have to have a negative slope whenever you have decay or decline. So to get my enrollment to go down 20 students each year, I need to write a negative 20. I'll change the appropriate variables. My output variable is supposed to be n of t, number of students, after t years. So I will replace x with t. Now normally we interpret the slope of negative 20 as being every time x goes up by 1, y will go down 20. With my new variables, that will be described as every time time increases by 1 year, my enrollment will go down 20 students as described in the problem. So just as a plausibility check, make sure that since it said decreases, your slope is negative, and the fact that it was the same number of students each year instead of the same percentage each year, we used a linear model rather than an exponential. In part D, the enrollment is decreasing by 20% each year, and I noted that whenever something changes the same percentage each year, you have to use an exponential model, which is of the form y equals ab to the x. In exponential, it's the a value that's the initial, and we had an initial enrollment of 700. And you can use a formula to find b. There's a couple different ways of doing it, but one way is to use a formula that's slightly modified as compared to before. When we had growth, we used the formula b equals 1 plus r. But now that we have decay, I'm going to write that as b is equal to 1 minus r, where r is still the rate as a decimal. And as a plausibility check, I said before that you better make sure that b is bigger than 1 if you have growth. Now I'm going to say since we have decline, make sure that b is smaller than 1. So for decay, make sure your b value comes out to be smaller than 1. And then if you want to be careful, I'll also say that it's bigger than 0 because it has to be positive. Unlike linear where you had a negative slope, with exponential, b will never be negative. b is always positive, and if it's smaller than 1, you get decay. If it's bigger than 1, you get growth. So my rate is 20%. As I did before, I'll change that to a decimal. You could think of the decimal points to the right of the 0, and you move it to the left twice. 20% as a decimal is 0.2, or if you want, 0.20. If I plug that into the formula down here, the b value in the formula can be found by taking 1 and subtracting r, where you write r as a decimal. So you don't write 20 here, you write 0.2, or if you want, 0.20. So from this, I get that b is 1 subtract 0.20, which comes out to be 0.8, or if you want, 0.80. So that is the b value here that goes into the equation. I often like to summarize this to my students by saying, when you multiply by 0.80, you're finding 80% of something. So if you're finding 80% of the enrollment, that means that you have 80% of last year's enrollment, which means you've lost 20%, which matches the story given. Keeping 80% of your enrollment means that you've decreased 20%. As before, I will put the appropriate variables in. My output was supposed to be number of students as a function of time. So I better make it a function of time by replacing x with the variable t. This represents a charter school that starts with a population of 700, and a b-value of 0.80 means it is declining 20% every time t goes up by 1, and since time is in years, that means it goes down 20% per year. I hope you found this video helpful, and as always, I wish you the best of luck.